Hello, my name is Alaukik, and this is a pre-recorded presentation for the 2024 meeting of the Society for Mathematical Psychology. Today, I'll be talking about our work on a multiple threshold race modeling approach to evaluate the effect of response scale resolution on confidence judgments. As far as decision-making goes, especially that involving choices, speed, accuracy rates, and confidence ratings are widely used across literature. This is because they provide us fundamental insights into the cognitive processes behind decision-making. For example, work on memory and eyewitness testimony has historically used these indices regularly. On the practical side, studying the interrelations between speed, accuracy, and confidence is important across domains, be it the financial, personal, or the legal world. Because of their importance, there already exist well-defined models of decision-making which try to incorporate these factors together, and we base our modeling approach on one such model, the linear ballistic accumulator. So what is a linear ballistic accumulator? The model accounts decision-making by positing that when an agent needs to make a choice, they accumulate information in support of an option over time. So here, the y-axis represents the amount of evidence accumulated, while the x-axis represents time. Note that the model typically accounts for two options in a choice task, but just for demonstration purposes, I will only show how it happens for one of the options. The agent's prior support for the option is denoted as their start point bias, and the overall amount of evidence that is satisfactory for the agent to make this choice is quantified as the threshold parameter. Now, once the evidence accumulation process starts from the start point bias location, the LBA presumes that it proceeds linearly and that the rate of evidence accumulation is linear. That is quantified as the drift rate parameter. Next, even after the agent reaches the threshold to make the choice, some time passes between reaching the evidence threshold here and behaviorally reporting this fact, for example, by pressing a button here. This time lag is qualified as non-decision time. Finally, the overall time taken for the evidence accumulation process plus the non-decision time gives us the entirety of the reaction time. While this version of the LBA, linear ballistic accumulator, gives us a compelling account for speed and accuracy, it does not directly address how confidence factors into the equation. To account for confidence, that we lean on the multiple threshold race model, which adopts the LBA and adds to it. So the multiple threshold model, as we take it, is applicable in tasks where people indicate their confidence and decision simultaneously. Under the multiple threshold race model, we still have the LBA-like accumulators, one for each option, option A and option B. And whichever accumulator first reaches the threshold is the option that's chosen, just as before. However, Reynolds and colleagues proposed that confidence levels reported over this decision is created by mapping the relative balance of evidence for the two options. Specifically, the evidence space between the zero evidence and threshold points is divided up by intermediate confidence thresholds, such as the one shown here. Such that the more of these thresholds that are crossed by the losing accumulator, the lower the confidence the winning option has, and vice versa. So for example, note here that the accumulator for option B does not reach the intermediate confidence threshold, leading to a choice, a highly confident choice. However, if the situation was slightly different, and if the option B accumulator had actually crossed the confidence threshold, the agent would report low confidence. Thus, the MTR model incorporates confidence into the picture. This basic schema can be scaled up to n confidence thresholds, such that a reporting scale with 2K or 2K minus 1 cutoffs will create K confidence thresholds cognitively. So for example, if people are asked to report how confident they are about their choice on a scale with 6 options, which would mean 0%, 20%, 40, 60, 80, and 100% confidence. So if people are asked to report on such a scale, the cognitive accumulator will have five confidence intervals. So this is what that might look like. The accumulator for option B only collected enough evidence to land above the first threshold, but below the second one. And thus the decision maker here would choose option A with 80% confidence. Now, at this point, some key questions can be raised. Are the cognitive thresholds mapped evenly onto the confidence rating scales? For example, while 0, 20, 40, 60, 80, and 100 are equidistant numerically, are the cognitive thresholds also placed equidistant from each other? Another question can be, how does varying the granularity of the confidence scale affect this? Next, you can also ask, does task difficulty leads to low confidence judgments? Do more granular scales lead to long reaction times, which in turn, by allowing for both accumulators to collect evidence longer, lead to lower confidence choices? To answer all these questions and more, we conducted an experiment at the University of Florida with 52 participants and 400 trials per participant. We manipulated the difficulty of the task and granularity of the scale in a simultaneous confidence choice paradigm. So here's what the task looked like. Participants came to the lab in person and were shown this screen. There were blue and orange dots in the middle of the screen, chaotically dancing around. Participants were instructed to indicate if they thought there were more orange or blue screens on the dot, and simultaneously indicate their confidence over this decision. The left-hand side, they were to indicate this over using this scale, the semicircular scale up here. The left-hand side of the semicircular scale supported there being more blue dots, and the right-hand side supported there being more orange dots. Now, the exact location on either half of the scale was decided by the participants' confidence. Full confidence meant choosing the last bubble on the scale, and the lesser the confidence, the closer to the middle of the scale the response would be. So for example, if you were 90% confident on this screen that there are more blue dots than orange, you would choose the bubble next to 10. Next, task difficulty was manipulated by varying the proportion of orange to blue dots. It had 4 levels of difficulty. And confidence scale granularity was manipulated by changing the semicircular arced scale above. The 5 confidence scales had 3, 5, 11, 21, and continuous options, making the study a 5x4 experiment. Each participant completed all of the 20 conditions. Lastly, the responses were made on a touchscreen desktop computer with participants using their finger to select the appropriate response. Just to go over that here, that's what the 5 confidence scales looked like. 3 options meant having the option to indicate 0, 50%, my apologies, that's a typo, 0, 50%, or 100% confidence. 5 options meant having 0, 25, 50, 75, or 100% confidence, and so on. Okay, let's look at the results. First, we'll have some preliminary descriptive results to go over. We find here on this first plot traces of rampant overconfidence. On the y-axis, we have accuracy, and on the x-axis, we have the 4 difficulty conditions with number of orange and blue dots noted in the parentheses. Therefore, when the orange and blue dots proportion was 199 to 201, that's a difficult or hard condition. These results here show that accuracy, that confidence is way higher than accuracy, especially in difficult conditions. There is a much larger discrepancy between the histogram and the confidence graph. Confidence levels are not actually affected much by difficulty levels, as we can see by the black line here, the black graph being basically flat. So let's uncover this a little bit more. Turning to reaction time results and focusing on the middle panel first, we see that reaction times increase with confidence scale options, tapering off after a while. This is typical and follows Hicks' law of logarithmic increase in reaction time as the granularity of the response scale increases. In the other subplots, we have broken down the distribution of reaction times for each of the 5 confidence scales. Clearly, we get the typical right-skewed reaction time distribution. So that looks normal. Next, looking at confidence and scale granularity, we see that besides in the 3-level condition, people were quite confident across scales, around about 87% or so. The continuous scale was no different. Looking at the confidence distribution for each of the scales separately, we notice that people, again, are reporting 100% confidence seemingly disproportionately. Finally, to really get to the overconfidence bit, we evaluated people's calibration. Just as a reminder, calibration is the extent to which people's confidence actually corresponds to how accurate they are. So if you are well calibrated, your confidence and accuracy would go hand in hand. But if you're badly calibrated, one or both of them would not correspond to each other. So looking at this, we found that people were overconfident across different confidence scales. A perfect correspondence between confidence and accuracy would have generated data that would lie on this perfectly diagonal line. However, the real data, as these lines show, show rampant overconfidence. Note that calibration is better when people are actually accurate, so towards the high end of the accuracy scale. But for low accuracy, people's confidence is way overblown. Lastly, note that overconfidence decreases as the number of response options increase. When you go up from 3 to 5 to 11 to 21 levels and the continuous scale, the amount of overconfidence decreases. Now that I've highlighted some of our descriptive results, let's turn to fitting the multiple threshold race model. So just to go before getting into model recovery and parameter estimation, here's a breakdown of the 23 parameters our model estimated. Feel free to pause and take a look. The main thing I would note here is that we are having the model estimate the intermediate confidence threshold using a beta cumulative distribution function. We are fitting separate CDFs for each of the 5 difficulty levels, and each beta therefore uses 2 parameters to define itself. With all that in mind, let's look at the model recovery results. We did not conduct model recovery or fitting using the normal methods. We used neural networks. This is because classical methods like maximum likelihood estimation and MCMC are too inefficient. They take hours to fit. But since we had a generative model, we could create as much data as we like. And since the universal approximation theorem says that any functional relationship can be approximated, given enough data and given enough of a complex neural network, we leaned on using a neural network for model recovery and model fitting. So let's turn to that. Okay, we did exactly that, and here are the results for model recovery. In each subplot, the x and y axes are true and estimated parameters. As you can see, they are well correlated for most of the parameters. Thus, the model recovers pretty well overall. Now, turning to actual parameter estimates, we use the trained neural network to do that. You might note that the start point bias towards the orange dots is slightly higher than the start point bias for blue. We did have participants report that the orange dots felt slightly brighter to them than the blue dots, even though we had set both of them up to have the same brightness technically. Next thing to note here is that the upper thresholds do not seem to systematically vary according to confidence scale granularity. Again, 1 refers to a continuous scale, 3 to a 3-option scale, and so on. Next slide puts all of the threshold results together for better viewing. Here, the left panel shows the location of thresholds for each of the 5 confidence scales. The right panel shows the real data as the blue histograms and model predictions as the lines. In the left panel, the black dot is always the upper threshold, the threshold reached by the winning accumulator, and the colored dots are the intermediate confidence thresholds. Note that the threshold in the 3-option condition is unusually high, resulting in high confidence responses. Although looking at the right here, the model still doesn't do a perfect job in the predictions. So that's still a sticky point. Other than that, we see mostly equally distributed intermediate thresholds. It is notable also that even the highest confidence thresholds, besides those in the 3 and 5 option conditions, the highest confidence threshold lies quite a bit below the upper threshold. Finally, looking at the right panel, you can see the model having a somewhat hard time predicting the real data, sometimes over-predicting and sometimes under-predicting. A lot of the trouble it has fitting might be because it's not capturing the zero confidence responses very well. By that we mean when people are highly confident in the incorrect condition. So the model is struggling with the disconnect between the frequency of the incorrect responses and how confident people are. A result we noticed in the descriptive results section too. So to conclude, using the multiple threshold race model, we assess decision-making in a simultaneous confidence paradigm, finding that overconfidence existed even in difficult task trials. Reaction times followed the classic Hicks law, distribution across conditions. Calibration got better with increased number of response options. We mostly successfully fit the model using a neural network, and that model fit might have been impossible using classical methods. And the model identifies that it might have a hard time incorporating data when people are overconfident while being wrong. Well, with that, I'm just about out of time. And I want to thank all of you to listen along with the whole team. Please reach out to me if you have any questions or suggestions. Thank you.